Did you know that everything you see, every star, every planet, every grain of sand, makes up only about 5% of the known universe? The rest is a profound mystery, a cosmic ghost story we call dark matter and dark energy. We can measure their effects, we can see the gravitational pull of something we cannot see, and we can observe the universe expanding at an accelerating rate, pushed apart by a force we cannot explain. This isn't just a small gap in our knowledge. It's a fundamental admission that our understanding of reality is, at best, incomplete. So, what is this holy grail of physics? It's called a theory of everything. The name itself sounds impossibly ambitious, like something from a comic book. But the idea behind it is surprisingly simple and deeply elegant. Right now, physics is a house divided. We have two magnificent, powerful theories that describe the universe, but they don't talk to each other. On one side, we have Albert Einstein's general theory of relativity. This is the physics of the very big. On the other side, we have quantum mechanics. This is the physics of the very small. Here's the problem. These two theories cannot both be right, at least not in their current forms. They are like two different operating systems trying to run on the same computer. One of the most famous and perhaps most controversial candidates for a theory of everything is string theory. Think of a violin string. By plucking it in different ways, you can produce a variety of different musical notes. String theory suggests that the universe works in a similar way. Each different vibration of a fundamental string gives rise to a different particle. All the particles and forces we see in the universe are nothing more than the different notes of a grand cosmic symphony being played on these infinitesimal strings. However, for the mathematics of string theory to work, it requires something extraordinary. It demands that the universe has more dimensions than the three of space and one of time that we experience. Imagine a garden hose. From far away it looks like a one-dimensional line, but if you get very close, you realize it has a second circular dimension wrapped around its length. Another leading contender takes a completely different approach. It's called loop quantum gravity. What if spacetime isn't the smooth, continuous background that Einstein envisioned? Loop quantum gravity proposes that the fabric of space is not a seamless sheet but a network, a weave of finite loops of gravitational energy. To truly appreciate why we so desperately need a theory of everything, we need to visit the places where our current understanding of the universe utterly shatters. The two most famous examples are the heart of a black hole and the very first moment of the Big Bang. Where do we look for clues in this monumental search? We can't build a machine to see strings or quantum loops directly. Instead, physicists have become cosmic detectives. The evidence they believe is hidden in the light from the dawn of time, in the ripples of space-time, and in the behavior of the most enigmatic objects in the cosmos. The quest for a theory of everything is a story of brilliant minds pushing the boundaries of human imagination. It's a relay race of intellect spanning generations. These scientists are not just solving equations, they are asking the deepest questions a human can ask. Where did we come from? What are the fundamental rules of existence? We are entering an era where new experiments and observatories could finally provide the data needed to distinguish between these competing ideas and guide us toward the correct path. Future gravitational wave detectors, like the planned LISA, will be sensitive enough to potentially detect gravitational waves from the Big Bang itself. We find ourselves at a remarkable moment in history. Now we stand on the precipice of what could be the final leap, the unification of all physical laws into a single, coherent description of reality. The quest for a theory of everything is the ultimate expression of human curiosity. It's a testament to our unwillingness to accept "I don't know" as a final answer. The universe has been hiding its source code for 13.8 billion years. We're finally learning how to read it.